Welcome back to everyone. Design of foundation, design of footing. Today we are understanding the second problem, that is eccentric square footing. In last class we discussed about square footing. The load was vertical and concentric, but here eccentric load I am considering. Eccentric load, or the footing may be subjected to moment also. If the footing is subjected to moment, that also will consider it as a eccentric square footing. Okay. See, the steps are similar, the same steps only we are using. Total load, and the second one is area of footing, dimensions of the footing, upward soil pressure, bending moment. Till here conventional steps, and after that depth for putting up slab satisfying bending moment I take, depth satisfying one way shear I will take, depth satisfying two-way shear I will take. Out of these three, whichever is maximum, that I will consider, and steel calculation I go for steel calculation. Then after that I check the development length and I will finish the design. Now this is the problem. Design a square footing for the column dimensions 500 by 500 mm, carries a vertical load of 500 kilonewton and 27.5 kilonewton meter moment. Okay. The soil below the foundation has allowable bearing capacity 250 kilonewton per meter square, ABC. Consider M20 and 415. Okay. As usual, I will first write the data. Column dimension 500 by 500 mm, vertical load on the column 500 kilonewton, moment 27.5, SBC 250 kilonewton per meter square, M20 concrete and Fe415 steel. Then the total load acting on the footing will be axial column load, that is 500 kilonewton, vertically it is acting. I don't know the foundation, that depth and dimensions of the foundation, therefore I consider 10% of column load as a dead weight of the footing. Sorry, this is the footing. Okay, 10% as dead load, dead weight of the footing. Okay, that is your 500, 10% of this is 50 and total is 550 kilonewton. Now second step, we will consider area of the footing. Before considering this area of the footing, we will go and understand the concept of eccentricity, how it affects our footing. This is a concentric load. Here one load is acting, which is concentric because it is acting at the center of the footing. Therefore the stress, upward stress acting on the footing will be P by A, force divided by area, and this is uniform from one end to other end. When you come to eccentric loading, here you can see the P, instead of acting at the center line, it is acting away from the center line. This away we can say it as a eccentricity E, means some distance from the CG. Then for the study purpose I can analyze this way, that is P as it is I will apply here, and at the center, on this center line, I will act two equal and opposite forces. Of course this is P and this is P, and both are opposite to each other, therefore they get cancels. Structurally they don't cause any stresses on the foundation, but for the analysis purpose I can see this force P and this force P together, I can consider and create a moment. See, this is equal and opposite forces acting with a distance apart, therefore they cause one moment. That moment will be P into the distance between them, P into E, that is a P into E. P into E will be a moment and this load will be left alone here. Okay, means the whatever that it is shown here, that is a P which is acting away from the somewhat center of the footing, and this diagram and this diagram looks the same. Means if a force is given and moment is given, it is nothing but a force is acting with a distance E on the footing. Okay. When it is acting like this, then obviously we will get a more stress at one side and less stress at another side. Okay. Then when we work out with a theory of bending stress, then we will get this total stress as a P by A plus M by Z. Z is a section modulus, Z means I by Y. Now here the minimum one I can say P by A minus M by Z. Okay, this is the stress distribution. Okay, here whatever that E is there, that E will come into picture here in M. Okay. Think that this load which is eccentric from here, and think that this force is more away from the earlier one. Then if it is acting somewhat here, what happens? Then this stress will induce more, then this stress may become 0. This is reduces to 0, this increases. Okay, that we can see here. It is P by A plus M by Z, and this one is P by A minus M by Z, but which is equal to 0. Think that this P further it is away from the CG, then we may get this type of stress distribution. When this P comes further away from the CG, then we may get here positive stress, and instead of 0 here, it may come as a negative. This negative indicates that if P is applied somewhat very far away from the CG, then it may create somewhat tension in the footing, or otherwise footing will lift at one side. Okay, this we need to completely avoid when we design a footing. Okay, our footing should not lift up in one side and compress at another side. Okay, therefore we should completely avoid this one. It means that the negative stress, the whatever the minimum stress you are getting, it should not be negative. Okay, for that I will consider a critical case. This is a critical case where we are getting it as a 0, P by A minus M by Z equal to 0. This I will analyze here, that is P by A minus M by Z equal to 0. P by A means L into B, considering rectangle, minus P into E by I into Y, that equal to 0. This P by L into B minus PE as it is, I means BD cube by 12. Here in this case I considered eccentricity in one direction, that is in X direction eccentricity is there, but with respect to Y direction there is no eccentricity. Instead of this we need to observe. Now after simplifying this one, we will get E equal to B by 6. Means if eccentricity whatever we observing here, if it is equal to B by 6, then we will get a critical case. If eccentricity is more than E by 6, then we may get a negative stresses on the footing, or otherwise lifting up of the footing. Means in no case our E should be greater than B by 6. In no case this P should not be away from center with a distance B by 6. That we need to consider and we need to design. Coming back to the problem, area and dimensions of the footing. That Q equal to, we know, P by A plus PE by I into Y, stress, maximum stress, and there I consider Q as a 250 SBC given, and I substitute all the values which I know except B. Then B I will get 1.86. We will provide it as a 2 meter. That dimensions I can show here. This is a square footing, 0.5, 0.5 is a column dimension, and we will get a projection 0.75, 0.75 in all the sides. Means 0.75, 0.74, 1.5 plus 0.5, 2. Means this is 2 meter, this is 2 meter. Upward soil pressure. For upward soil pressure, as it is one-way shear means, one-way eccentricity. One-way eccentricity means it is eccentric only in X direction. Therefore, we don't get any variation in the stress in this direction. Okay, therefore we got a equal stress distribution from one end to another end, and with respect to this axis we are getting maximum stress here and minimum stress here. We can calculate this maximum stress as it is said in the equation only, that is a Q max in the previous theory, P by A plus M by I into Y. P is a 500 and 2 into, here we are not adding any dead load of the footing. Okay, that here area we are considering provided area. Then we will get 145.62. Then Q minimum P by A minus M by I into Y. Same substitutions we do here, and 104.37 kilonewton per meter square. Then what about this uniform load? That is 500 divided by 2 into 2. When this is acting here, that is 500 divided by 2 into 2. We are getting equal 125. Then we will make factored load here only, so that we will not multiply 1.5 to the moments and shear forces in future steps, in further steps. Okay, here only for this 145 I multiplied 1.5 factor of safety 218.45. For 104 1.5 is multiplied 156.55. For 125 1.5 is multiplied 187.5. Those we can show here 156.55, 218.45, 187.5. Now bending moment. Here we will observe critical section will be at the face of the footing only as per the IS code. Previous problem I have explained. Okay. Considering this section, this part of the footing, this acts as a cantilever and the critical section will be this one. Then this much load is which is 187.5 which is acting cantilever. Therefore moment will be cantilever formula 187.5 into 1 into L square by 2. WL square by 2. Then 52.75 kilonewton meter I got a moment here. Then coming to the bending moment in a second portion, that is this portion I consider, and again this acts as a cantilever, but here uniformly varying load is there. I can consider this load as one rectangle and one small triangle, but I know this entire dimension, that is 218.45, but I don't know this dimension which is at the face of the footing. For that I will consider the same diagram here. I will put this portion, small portion, as x only, but however this I know this is 156.55 and the same will be here, and the left out will be 218.45 minus 156.55. I will get 61.9. This is 61.9, this is x, and this is 2 meter, and this is 0.75 plus 0.5. Okay, therefore I will interpolate this one, or by using similar triangular method I find x value 38.65. After this is 38.65 x and this is 156.55. 166.55 plus x will be 195.23. I got the total dimension from here to here. Means the UDL of rectangle, UDL load of this much value is acting, and one more triangle is also acting. The triangle value is 23.21. How? 218.45 minus 195.23, 23.21 I got. Means one UDL and one triangular load which is acting on the projected area, cantilever. Okay. For that one I will calculate. For this UDL, WL square by 2, W is there, L square by 2. This rectangle is over. But when coming to the triangular load, this triangular load, distributed load, triangularly distributed load, I will make it as concentrated load by taking a area half into this height into base. Okay, that I will get, and into the distance, its CG will be here, from here to here it is 2/3 of 0.75, then I will get 59.26 kilonewton. And the third portion here I can see here again small one rectangle is there and one triangle I can see. Here I don't know the value of this one, therefore I have to interpolate here, considering this portion as a y. This I know. Okay, this portion y, and consider the big triangle here, y equal to 23.21. Then this 156.55 plus 23.21 total I will get here, and here 156.55. No need to add them because we will however calculate rectangle separately and triangular separately. For rectangle we have WL square by 2 formula. For triangular, load into perpendicular distance. Then we will get 46.20. Now depth for bending moment satisfaction. We have 3 moments, M1, M2, M3. Out of these 3 we will consider a maximum moment for depth calculation. Okay, if depth calculated for this moment can definitely will satisfy, the depth which is calculated by using 59.26 will definitely satisfy the moment 52.75 and 46.20 because they are very small compared to this one. Now depth equal to this moment, maximum moment, into that basic formula I will write and I will calculate depth. 146.5 mm I got. I will round out to 200 mm. Now depth footing slab for one-way shear criteria. One-way shear criteria, we will go to the basics, that is a 0.36 FCK bxu equal to 0.87 fy ast. This step easily means detailedly explained in the previous problem. You can go through that, and through that we will get a percentage steel 0.96, and this 0.96 we will see here and we'll interpolate, and we'll get for M20 tau c value as a 0.61, and we will consider tau c equal to tau v, determine d. Obviously that d will be safe with respect to that because we are putting d as unknown and we are solving. Then in that case we will write tau c equal to this one. But here the critical section as per the IS code is from the face of the column we need to go at a distance d from the face of the column, but we don't know this d, therefore we will put that d unknown, okay, because we want to determine that only. And one more problem which comes here, that is this is a trapezoidal load acting here, but this trapezoidal load, calculation of said trapezoidal load is very easy, but keeping this dimension d and calculating this trapezoidal load, it becomes very complicated. Therefore for safer side also and for computation to make computation easy also, I consider this as a full rectangle, even though I don't have a triangle here, but I assume that there is a triangle and it is a UDL from top to bottom. Okay, then I will calculate this 218.45 as it is. Then I will put this value 218.45, this value, and this distance of this blue strip is total. This projection from the face of the column is 0.75 minus d, that is your 0.75 minus d, divided by bd, that is b is 1 and d is d. Then I will substitute tau c equal to 0.61 into 10 raised to 3 is for unit conversion. Then I will get d equal to 197 mm. Then I will round up 197 only, but in previous for bending moment we provided 200 mm. This is 197 mm, therefore it is safe. Coming to depth of footing for to satisfy two-way shear, it is a two-way shear, okay, and in previous lecture it is completely clearly explained. Please go through that video and you will come to know here why we write this 1.12 and these all formulas and all. So directly I solve this one, d equal to 300 mm, I got 240 mm, and 60 mm cover I will add 300 mm. Then out of these three moments, then we will calculate AST. This is AST formula. Common AST formula is 0.5 FCK BD by 415, 1 minus root of 1 minus 4.6 m divided by FCK BD square into 10 raised to 6. And here B is 1000, D is 240, and FCK 20, and Fy 415. And these values we will substitute here. First moment AST1 will be corresponding to M1, that value is 645.03, and AS2 will be corresponding to M2, that value will be 730.03, and corresponding to M3, AST3 will be 558.04. I got steel, but we will check with the AST minimum. AST minimum formula given by IS code is 0.85 by Fy into BD, that is 0.85, 415,000 into 240, we got 491.56. Now see, this 645.03 is more than this one, therefore safe. 730.03 is also more than that, correct. 558.04 is also more than that, correct. If any moment, if any AST, if it is less than this one, then provide this one, ignore that one, okay. Now coming to, then based on that, based on these AST, you calculate spacing, that is consider 12 mm diameter bar and calculate the spacing. These are the spacing, that is 0.785 means pi by 4. This is a d square divided by total AST into 1000. For first AST I got 170 center to center. For second AST 150 center to center. For third AST 200 center to center. Okay. Now coming to the development length. Coming to the development length, as it is explained in the previous class, for 12 mm diameter we will get 452. That we this much should be available, should provide, but available distance is from this end to this end. Total is 2000 mm minus 500 divided by 2 means projection I got. From the projection I will get a 50 mm reduce here a cover, then I will get 700 mm. This is 700 mm available, but we need to provide 452 mm, therefore which is safe. In diagram you can show here, as this is eccentricity here, this is a heavy section, therefore you will provide the AST here a different one. These bars will be continuing from this end to this end with a spacing 150, and these bars will spread from here to here with the spacing 200. These bars will spread from here to here 170 mm center to center, this 170 mm center to center, and development length is this much. Okay, thank you. In next class we will consider rectangular column footing.